Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Breeze Block Wall Design. My name is Amanda from Engineers Australia. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's long-standing industry partner, Brickworks. Brickworks Building Products is one of the world's largest and most diverse building material manufacturers. Brickworks has built an enduring reputation with customers and is highly regarded for its innovation, professionalism, and ever-dependable products and services. Today, we will hear from three speakers, Thomas Chan, Olsen Lee, and Kathy Inglis, followed by a live audience Q&A, and I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to welcome our first speaker for today, Thomas Chan, Senior Design Engineer at Rickard Engineering. Thomas is a structural engineer with international professional memberships in Australia, the UK and Hong Kong, and currently is the Senior Design Engineer at Rickard Engineering. Thomas's work is focused on structural engineering and facade engineering. He has extensive years proven experience in design offices, client-side project management offices, and on construction sites. Please join me in welcoming Thomas Chan.
Thank you very much for Amanda's introduction. So also thank you Brickworks and Engineers Australia in inviting me to participate this breeze block masonry walls to present the structural design and development. So let's start. So today's presentation will be divided into two parts. The first part will be presented by me, including the design brief, applicable standards, design parameters and reference tests, analysis methodology, and the second part will be presented by my colleague, Elson. He will present the unreinforced masonry design, reinforced masonry design, and he will also give you some example using the design charts. So we commence the part one. Design brief. So our goal is to develop this design charts and technical document for the masonry breeze blocks, which is in accordance with Australian standards, codes, and practices. And these design charts, we are going to give the users able to be understood by non-technical users, for example, the designers, the clients, so they can preliminarily study what kind of bricks and what pattern of bonds and approximate early understand what types of supports they use and have their early planning. But more important, we also provide information for technical users such as the structural designers and facade designers to produce common breeze block wall designs. So when you start to design a breeze block wall, probably you have few questions to ask. Say, if I choose a breeze block type, what bond pattern can I use? So can I use stack bond or a stretcher bond or any other type? So second question is, how do I support it? So there are a combination of supports from bottom, top, or side supports. You may have 4 side supports, with 3 side support with the top is free, with 3 side supports with the side, one side is free, or 2 side supports, which is the top and bottom, or left and right supports. So among of these variations, what is the largest wall in height and width you can build? So applicable standards. So we designed a brick block wall in accordance with the Australian standards. The first one is the most important. The basis of designs is 1170 series. Part 0, the general principles. Part 1, permanent, imposed, and other actions. Part 2, which is the most concentrated part in our design, is the wind actions. And in some cases, if you build a house, probably you can use the Australian standard 4055. And because breeze brick is a masonry material, we mainly designed it to the Australian standard 3700 masonry structures. But we also reference to other design standards, such as the Australian standard 3600 series for the concrete structures, 4100 steel structures, and the cold form stainless steel structures, AS 4673. And the steels and stainless steels are mainly for the wind post designs. And be careful that this list is not exhaustive. For example, those standards for screws, bolts, etc. are not listed here. Design loads. So this brick block wall is considered as a building finish able to resist lateral loads. So mainly we design brick block wall as a facade. And it could be used internally or externally. And we designed it to make sure it has the adequate structural capacity in flexure, which is the bending due to wind. So the wind pressure is very important in here. So it's assessed, as I previously discussed, is the 1170 Part 2 or 4055 Australian standards. So you need to calculate the internal pressures, the external pressures, and also, if applicable, the breeze block porosity. So this porosity factor is excluded in our design, which will be discussed further in the next part. So other design loads. So apart from the wind loading, the following loads should be assessed as per project basis. The first one is impact load. So this impact load is a load with a punching effect on the wall, which punch through. So we need to consider this as a project basis if necessary. The second is the barrier load. If you want to design the breeze block as a protective barrier, for example, like a balustrade, the barrier load need to be designed by the competent structural engineer or facade engineer per project basis. The third is seismic load. Seismic load is not included in our design chart, so if necessary to be considered, it also need to be assessed per project basis. So other structural applications such as load-bearing walls or shear walls are also not included. So we don't include any external load applied to the breeze block wall except the lateral window in out of plane directions. So in plane shear or any gravity loads loading from above to make it as a load-bearing wall should be designed and checked by a competent structural or facade engineer. So design parameters and reference tests. Before our designs, we have reviewed Brickworks product manual. This is one of the samples showing the cloud breeze. It shows the dimensions of the brick, the self-weight of the brick, but the most important in here is the unconfined compressive strength. However, there is one important parameter not in this product manual. So we have done a series of tests to find it out. The most important design parameters is the flexural strength of the brake. So in the past years, Queensland University of Technology has done a series of flexural strength tests on the brakeworks. Also, the University of Newcastle has done flexural strength and bond range tests of each types of breeze brakes. They are all in accordance with Australian Standards 3700 Appendix D. So all these brake design and tests are compliant with the Australian standards. And as you can see from the photos, we have done a large samples of test specimens for each type of breeze block. So we can use the large amount of data to calculate the characteristic strength of flexural design parameters. After we have done the test, and before we go to generate the design charts, we have a preliminary investigation on the breeze block. We have done a series of finite element models for each type of block to understand the large variety of the block geometries, the load path within the block, stress pattern, and the most important is we compare the test results and design manual data with these finite element results and find they're comparatively reasonable. And the test result could be used for the further next stage design. Analysis methodology. So the design principles is in accordance with Australian Standards 3700. We have unreinforced designs, which is designed with consideration of masonry and mortar strength only. We have also designed it as a reinforced blockworks. It designed with consideration of masonry and reinforcement. And in accordance with Australian Standard 3700, Clause 4.6, there is a minimum robustness requirement of 0.5 kPa. So in our design charts, we provide the minimum of loading to 0.5 kPa as a minimum for the users to do the design. And the upper bound of the wind pressures, we choose to design up to 4.5 kPa without the porosity factor. So if you include porosity factor in it, the allowable design basic wind pressures could be even higher. And this wind pressure should cover most of the design cases in Australia. However, if you have a wind load more than 4.5 kPa, and it should be assessed on a project basis with a competent structural engineer or facade engineer. So, design assumptions. This is very important for the designers to understand what assumptions have been made in the design charts. First, as I said before, this design charts for the breeze block works is a non-load bearing wall, so there's no superimposed compression from above. At the supports, we assume there's no rotational restraints, which is a pin support. We always assume a 10 millimeter bed joints at per pans. And M4 mortar is assumed. And we design for stretchable and stackable only. So there's basically no openings. If you design a wall with an opening with certain area without any breakworks or breeze block, so this is not covered in this design. As I said before, impact resistance has not been assessed, neither for the barrier loading. And the most important also is the porosity factor for wind load is not included. So in the next part 2, my colleague Alison will talk about this as an example. So grouping for designs. So breeze block there are 8 different types of breeze: circle, flower, kite, linear, cloud, diamond, wedge, arc. So we group them to simplify this design charts and minimize the number of charts we need to produce. So we group them based on block depth, which is the wall thickness, the overall shape, which is the square or rectangular, the dimensions of the breeze block, internal geometry, special arrangements. For example, the kite breeze could be a double skin, which is a back-to-back double layer, or breeze block placed vertically or not, or horizontally. And sometimes we have some custom thickness, which is cut from the standard thickness. So after a study, we have grouped into mainly 6 categories, or 7 actually. First group is a square in 90mm thick. We have circle and breeze. Rectangular in 90mm thick, including diamond breeze, which is a tailor-made, cloud breeze, and wedge breeze, also non-standard thickness. Rectangular in 140mm or 70mm. So 70mm is a custom thickness cut from the 140 standard. This includes diamond and wedge. Rectangular 180 thick, which is the arc breeze, kite, double skin or single skin, and linear. So the main purpose of this grouping is to minimize the number of charts, as I said before, but also this will give you or give the designer, particularly the architect or the interior designers, the flexibility to use different breaks within the group, because we generate or design the breeze design charts for a single group with the most critical characteristic design parameters. That means within the same group, you can max use those different breeds in that group to allow you the most flexible designs is aesthetical. So design flows. Based on the design parameters, assumptions, and grouping I said before, we design the charts and with calculations to Australian standards 3700 with different wind loads, wall dimensions, bond patterns, support conditions, and different wind post designs. So all these different requirements, we have produced nearly about 120 design charts. So here are 2 sample design charts, and Alison will talk about this in detail in the next part. So when you start the design of breeze block wall, you need a layout height and width of the breeze block. And then you can choose the bond pattern. And then choose your breeze block type. And then you need to figure out how many and which side can be supported. And then also determine the design wind load. And based on the manual, you need to choose it as an unreinforced or reinforced breeze design. And the support options like wind posts or sound supports from structural or anything else with the supports that's appropriate for your design wind load. And then you can check from the chart what wall dimensions allowed and whether this comply with your allowable or with your layout design height and width. Other design considerations. So apart from what I said before, there may be some design considerations not included but need to be considered in the breeze block wall designs. The first one is the control joints. So control joints probably may be needed for building movement considerations. So basically, we follow common masonry facade rules. For example, the foundation movement or on articulated walls, like the one showed on the right-hand side of the slides. The second probably somehow is the beam deflections or column when wall shortenings, etc., or lateral movement of the building structures. The second is the thermal movement. So you also follow common masonry facade rules for thermal if considered necessary. Masonry swelling if necessary as well for kite brace, because kite brace is not a concrete brace. So if it is considered necessary, you may allow swelling movement from the bricks. So applicability of using brace block porosity. So sometimes say for a certain usage, based on the Australian standard, whether you can use the porosity to calculate the porous cladding reduction factor, so give you a more efficient design, or particularly for freestanding walls, you may have a different porosity factor. So brace block corners. If you have a corner with two sides of brace block designs in orthogonal directions, and the walls support each other for lateral wind, which means one side of the corner will support the other orthogonal direction in a horizontal axial capacity. This should be assessed as a project basis. Brace block fully freestanding walls. This one is not included in our designs, but it's necessary. The cantilever supports need to be project basis designed to achieve a 2 or 3 side supports, but the infill block wall may be based on our design charts to give you a brace block wall designs. So thank you very much. This is the end of the part 1, and I will pass the presentation to my colleague, Elson. Thank you very much.
Thank you, Thomas, for your input. I'd now like to welcome our second speaker for today's discussion, Olsen Lee, Design Engineer at Rickard Engineering. Olsen Lee holds a degree in Civil Engineering with Architecture from the University of New South Wales with a strong passion for structural mechanics. Olsen is currently a structural design engineer at Rickard Engineering, focusing on facades and bespoke engineered systems across many high-end projects. Olsen specialises in the design of structural aluminium and glass, including curtain wall facades, in addition to glass fibre reinforced concrete, GRC, masonry and natural stone cladding. Please join me in welcoming Olsen Lee.
Thanks, Amanda, for the introduction, and I'll be doing part 2 for the Breeze Block Structural Design and Development, going through more of the details of our design. So let's begin. Okay, so first section that we're going to start off with is the unreinforced breeze block design development. Now, we've separated this into 2 components, unreinforced and reinforced designs. So for each category, we have different bond patterns that you're allowed to use, which I'm going to go through shortly. So first up, the design principle behind unreinforced breeze blocks. So as you can see, we're starting off with a stretcher bond wall. And the principle that we have to assess is, looking at what kind of failure planes that we expect from loading. So this is out of plane loading, primarily focusing on wind loads, which is a uniformly distributed load. Now, this is obviously based on the support conditions. So cracks generally develop at areas of high stress. Now, from flexural behavior, we know that the areas of higher stress would tend to fail first. So in this case, when we have top and bottom supports, we are bending in the vertical direction. we go, supported top and bottom. And when we are loading this wall, we're expecting a failure plane horizontally along the mortar bed joint. Now, this is important it's important in a few ways. So the bed joint is the most critical aspect of most of our designs, both unreinforced and reinforced. So we're looking for ways to address this weakness and how to strengthen and build walls. So this is resisted by the flexural strength of the mortar. Now, as I've just said, the weakness is in the mortar. But the reason why it's so weak is because mortar is not very great in tension. So the flexural strength of mortar, which has been tested, as shown by my colleague Thomas previously, is quite low in most circumstances. This is counteracted by the self-weight of the blocks above, creating friction and counteracting this tension force. Now, we have elected to include this parameter inside our block design, whereas usually it's ignored just for conservative, as conservative design. So this will add an additional few percent of capacity because the capacities were not great to start off with. So now when we're looking at the horizontal direction, so wall supporting on either side. So again, in stretcher bond, but this time the failure plane we expect in a slightly different manner. So the first one is what we call a zigzag pattern or a cogged crack. So in the diagram, it is illustrated as not in the center. So if you were to imagine the cog crack forming within the center of the wall, so in the midspan, so this one's just for demonstration purposes, it is failing along the mortar joints. So the mortar bed joints, which are the horizontal ones, and the mortar perpends, which are the vertical joints. In some cases, which is especially more pronounced in the breeze blocks, is a failure plane along the perpend joints and also through the masonry. It's kind of like a straight crack through the whole wall. So this failure is dependent on both the mortar and the block strength itself. So following on this, our breeze block specific consideration, which is atypical of a normal bond masonry wall. Now, as stated previously, it has a weaker section than typical masonry, reduced horizontal bending capacity. And what do I mean by that? We need to identify the weakest plane in each block geometry. So for each type, we are trying to identify where we expect the flexural failure to occur. Now, there are simple examples, so I'm going to start off with the circle here. Obviously, the weakest failure plane would be within the center of the block. But for more complex geometries, it may not be so obvious, such as the flower. So one might point to say that the failure plane might be within the middle. But others may say that the point of failure might be slightly towards the edge. Now, through our finite element studies, we have identified the critical failure plane and have designed design charts based off of that. So going through one more example, say for example, the cloud breeze. Again, the center failure plane is the most obvious to consider, but how about an off-center failure plane? Or in the case where we're doing a vertical configuration, such that to induce a different direction of bending, we may also consider a horizontal failure plane like this. Now, unreinforced walls must be stretcher bond only. So the reason for this one is due to design requirements from AS 3700. Now, stack bond has no horizontal bending resistance in accordance to 3700. And the reason is because of the perpend spacing factor, to be more technical. But there is no allowance in the code to allow you to make an unreinforced stack bond wall. So stack bond cannot be unreinforced and must be reinforced, which will be addressed in the following section. So now you may ask, okay, we've gone through simple one-way spanning walls, either top and bottom support or side supported. So for two-way spanning walls with a combination of supports is obviously a combination of vertical and horizontal bending, similar to a design of a two-way slab. So this can be designed using the virtual work design method in accordance with 3700 2018, and has equations to incorporate both horizontal bending and vertical bending components. Okay, so we have 3 and 4 side supported walls. And what tends to happen is that we get a more complex failure mode, namely diagonal cracking patterns in addition to the vertical and horizontal cracks. So our idealized crack pattern for our analysis will obviously depend on our support conditions and our wall aspect ratio. Now, as we've just went through, for 3 side supported with the top edge free, we're expecting a failure mode similar to the diagram shown, with a diagonal crack and then a vertical crack splitting towards the free end. A similar failure pattern can be observed when the side edge is free. So imagine you've rotated it by 90 degrees. Obviously, the asymmetry from this is due to the slightly asymmetric nature of our blockwork example, but these are obviously idealized crack patterns, which is just to show the idea of failure, or what we expect. And finally, we have 4 side supported, which will exhibit almost fully diagonal cracking patterns depending on our wall aspect ratio. Now, for those who are interested, there is great further reading and documentation, both in the 3700 supplement 1, which details research and the virtual work method, and also from the Think Brick technical manuals, which have it's a fantastic resource with many examples and technical information. So let's have a look at how we developed our unreinforced stretcher bond design charts now, because we know that we cannot build unreinforced stack bonds. So we have charts for 2 side supported, which in general is for internal applications only due to the reduced capacity of these walls. However, once we introduce another support, so namely with the top edge free or with the side edge free, we can have greater capacities which will be able to scale into external conditions. So these will be our most common applications. And if you are fortunate enough to have all 4 sides supported, we have charts for that as well. So we haven't really gone through what a support is actually considered as. So a support is considered if a lateral restraint is provided. So we're assuming no rotational restraint, which for those interested will increase the capacity in accordance with 3700. So increase one of the factors there. But for the sake of the design charts, we have assumed everything as purely pinned at all supported edges. And another consideration, which was touched upon before, is a maximum length, well, we say typically 5 to 6 meters for control joints, for building movement, swelling, and etc. Now, hopefully that gives a good overview of the unreinforced breeze block. And we're now going to do a design example. So, for example, I want to build an external detached feature wall with the wedge breeze blocks using stretcher bond. So I want to support my wall on 3 sides with the top edge free. And an engineer has assessed my wall, or you have performed the wind loading assessment yourself, for an ultimate wind of 1.5 kPa. Now, the design constraint I want to enforce is that my wall length should be 3 meters. So how high can I build? Now, we'll look at the appropriate design chart per the design manual. And in this case, it would be the wedge breeze block in stretcher bond, 3 side supported with the top edge free. And we'd look at a chart that looks like this. So now zooming in, we are now trying to locate the point for 1.5 kPa, and also with the restraint of 3 meters in length. So we'll be looking at this point here. And this is quite straightforward to look up. We can now observe that the height that we can build for 1.5 kPa will be 1.6 in height. So the total wall without the porosity factor will be 3 meters by 1.6. So since this is part of a freestanding wall, the designer may consider the porosity factor, which is further described within the Australian Wind Code 1170.2, which is the freestanding wall porous factor, porous cladding reduction factor. So we've calculated this beforehand based off of the porosity of the wedge breeze, which gives us a factor of 0.8. So the designer may choose to reduce their wind load by this factor. So now it would be 1.5 kPa times 0.8, which would give us 1.2. And we can design for this reduced wind load due to the porosity of the brick, the breeze block. So let's re-look at our chart. Again, 3 meters in length, but now designing for 1.2 kPa and looking at our increased height that we can achieve. So now we have 3 by 1.9 dimensions which are allowed. Okay. So for the second portion, we're going to design reinforced breeze blocks and the design development of that. Now, reinforced breeze blocks. The reinforcement shall be provided at every bed joint. Now, we don't have much choice in terms of where we provide reinforcement for breeze blocks. So the obvious location is going to be for the bed joints and horizontally laid, because we're building the breeze block walls from the ground up. Now, this is limited by the 10 millimeter bed joint, the 10 millimeter bed joints. So as a standard kind of width. So we have investigated off-the-shelf products such as Ancon AMR ladder style bed joint reinforcement to be able to carry these out-of-plane loads as a reinforced section. Now, the way we are going to design this is as a one-way horizontally spanning wall to simplify. Now, the astute of you may be saying, okay, the bottom of the wall must be supported generally because that's how the wall is going to be standing. However, for simplification purposes, we will be designing simply as one way, as conservative nature and for ease of calculation. So we assume no fixity at the bottom. Now, the reinforced masonry design will follow general concrete principles. So it's essentially similar to flexural design for concrete. Now, as you can see from the diagram, we have our stress block diagrams with the strain limit, our parabolic stress distribution, and our equivalent stress, our equivalent internal forces. So the masonry acts in compression only, similarly to how concrete acts in compression only in reinforced concrete design. And the reinforcement will act in tension to resist that internal bending. We are going to utilize cracked section analysis where necessary and use stress block equilibrium as was just discussed. And we also have to have consideration for ductility and ductile design to ensure that the wall will fail safely and not in a brittle manner. Now, there are some masonry specific calculation parameters per the 3700 code, which we should be aware of, which is the equivalent rectangular stress block, which is slightly modified from the concrete code, and also the compressive strain limit, which is slightly higher, it was 0.0035. And we have also double checked using the deemed to satisfy flexural strength method within 3700, just to double check our calculations. Now, how does this really translate into the breeze block design? So we have considered design strips as so. And the limitation of which is only having reinforcement within the bed joints, as we've said previously. So this would be a cross-section of the diamond brace reinforced section with the bed joint reinforcement, for example. So you can see the section marker there with our corresponding section. We will also have reduced compressive capacity due to the section being hollowed out in some portions. Now, this is especially important with our finite element study to see how the stress is developing and to see where the load is transferring in flexure. Because obviously, we are relying on our masonry to carry this compressive load and our tension reinforcement to carry the tension. And this is going to be a doubly reinforced design. Okay, so just as a side note, there is generally no distinction for stack bond or stretcher bond reinforced design. So we're counting the compression block as to be identical, and any additional strength gain from stretcher bond is ignored. And we are saying that the reinforcement strength dominates this behavior. So let's have a look closer using the section, so rotated here. We are taking a slice of our diamond brace as our design section and applying our reinforced masonry or reinforced concrete basics with the modified parameters to be able to achieve our ultimate flexural strength. So as expected, the capacity is dominated by the brace block thickness. And in our study, we've further considered 5mm, 4mm, and 3mm diameters, which are off-the-shelf products from Ancom. So how does it work as a system? Now, since the brace block is spanning horizontally, we need to provide fixity in the form of some vertical columns. So one such choice is going to be adding reinforced blockwork columns, which are spanning vertically. So in this sense, we're saying columns in that they're vertical, but really in design, they're acting as a beam, so a flexural beam. So the horizontal bed joint reinforcement will lap with this to form a system. So as you can see from the diagram where the force will transfer, firstly horizontally and then vertically into columns, and then have reinforcement lapped to ensure that we develop our stress and develop our force transfer. And this reinforced blockwork design is typical of 3700. So this is fairly straightforward. We can refer to other sources for this. However, we also need to check the stiffness of the column. Now, this is essential in that we need to have sufficient stiffness in order to say that this assumption is correct. Now, the reinforced blockwork column deflection is checked using crack section analysis, which is not typical in the standard. And we've used some additional materials to check this. So as a 3D system, let's have a look here. We have our stack bond brace block wall with bed joint reinforcement, and hatched in red here is going to be our blockwork columns in quotation marks. Now, these can be however many blocks wide, up to a limit of 4, and obviously up to the discretion of the designer to see if the dimensions look applicable for our load case. So obviously you can't just say 8 blocks of reinforced is going to be acting as a single column. Now, another choice that we have, which is probably preferred, is going to be wind posts. And they're going to be concealed within the perpen joints of our brace block wall. So these can either be in stainless steel or hot dip galvanized steel, depending on your corrosivity category and your corrosion rating service life. And it works in a similar manner. So firstly, we have our bed joint reinforcement, allowing the brace block wall to span horizontally. And then this in turn transfers the force into the wind post, which will span vertically. So the detail of which is going to be a little slotted connection. We have brick ties slotted in between these wind posts, allowing the transfer between the bed joint reinforcement and the wind post. This will allow us also to have a continuous and seamless wall. which we can't really achieve using reinforced blockwork columns. And another detailing thing that we have to care about is that there should be at least one block at the end to cap off. So you can see here on the left-hand side, there's one extra block. And here's a look at 3D. So just to make sure it's a bit more clear, we've got our horizontal bed joints, our stack bond, and then we have our wind posts in between with the slots. So please refer to the manual, which has more information on this. Okay, so reinforced breeze block design charts. In essence, in essence and in summary, we are firstly designing the reinforced breeze block wall to be spanning horizontally between the supports, and then designing a vertically spanning supports to transfer the load back into the primary structure. Now, this can be in the form of reinforced blockwork or in the form of wind posts, either stainless steel or hot dip galvanized. A further check is required to ensure we have sufficient stiffness, so we can we can make sure that our assumption is correct, such that they act as supports. And essentially, our design charts will be governed by these several parameters. So firstly, the breeze block capacity spanning horizontally, the capacity of the vertical supports, the stiffness of the vertical supports, and lastly, our control joint positioning, which will limit our wall length. Okay, so hopefully that was a good overview of our reinforced breeze block design development. I will now go into some examples to show how to use our design charts. Okay, so now let's go through some reinforced breeze block design examples. So let's start off here. Our design example 1, which is with reinforced blockwork columns. Now, I want to build an external non-load bearing wall with arc breeze blocks using stack bond, which is part of my house. Now, this is an important side note which we'll go through in a second. I must use bed joint reinforcement because it's stack bond, and I want to use blockwork supports, 2 blocks wide. So the design ultimate pressure that is determined in accordance to the wind code is 2 kPa. And my design constraint is that I want 4-meter sections of arc breeze blocks. How high can I build? So now let's look from the manual and refer to the correct chart, which is as follows. Arc breeze, stack bond with 790 wide reinforced blockwork. Now, what is the 790 referring to? So let me zoom in first. 790 is referring to 2 blocks wide of typical 390 wide core field blockwork. Reinforced typically with 2N10 or 2N12 and 25 MPa non-shrink grout. So now let's look from 4 meters as our blockwork column spacing, referring there, up to 2 kPa and reading across. So without the porosity factor included, we have a limitation of 2.1 height of our wall for as many bays as you'd like, without the control joint requirement. That's all right. So 790 wide blockwork at every 4 meters max spacing. So at centers and control joints to suit. Now, since this is not specifically part of a freestanding wall, so the note here is that it is an external non-load bearing wall, which is part of my house. So because it's considered part of my house, it is up to the designer, as is not explicitly stated in the wind code, not without a wind tunnel test, say for example, to use this porosity factor. So this is down to engineering judgment if you want to use the increased capacity. For detailing, so there's good diagrams in the manual that we can refer to. So I'll quickly just go through this one, is that we have typical core field blockwork, N10, 2N10 or N12 each block, up to 4 blocks wide. Of course, the designer has to look at the relevant conditions to see if it is applicable to assume that this single 4 block wide column can support our breeze block wall. So 4 blocks is approaching the limit, 5 blocks, it's difficult to say. Now we're assuming for pin joints for our block work. So we're going to have dowels to structure, top and bottom, and movement joint at the top if required. Now this is especially good because it is compatible with other GB masonry products, which is in the same family as breeze blocks. So all these products can be used together. So now let's look at our second design example using wind posts. So in this case, I want to build an external screen with circle breeze blocks using stack bond. I also must use bed joint reinforcement because it's in stack bond, and I want to use these concealed wind posts for the seamless look. The design wind pressure that is determined using the wind code 1170.2 is also going to be 2 kPa. The constraint is that I want my screen to be 1.75 meters high. Now, how many wind posts do I need and what centers do I need to space them at? So let's refer to the manual and look at the chart corresponding to this case. So I have circle breeze, stack bond, and using stainless steel wind posts 10 millimeters thick. So I've elected to use stainless steel in this case due to my corrosion category. So zooming in here. So let's read. So again, I want to read for 2 kPa that I have, without a porosity factor, 1.75 meters in height. So the steel stiffener spacing is going to be 0.7. And these are going to be 10 millimeter thick stainless steel wind posts. Okay, slightly misread there, at 1.8 meters and its max. So that's approximately every 6 breeze blocks, which is good for constructability. So obviously we're going to have to round it down in the case it goes in the middle of the breeze block. And we have control joints to suit again. Now, in the discussion of porosity, we have to assess using engineering judgment if the porosity factor can be included. Now, in the case of an external screen, it may be decided by the designer that the porosity can be included, but it really depends on the distance between the screen and the structural wall behind, or say, for example, a window. So for detailing of the wind post, more to be found in the manual, as a disclaimer here, is that our system will also allow up and down movement tolerance. So this is the wind post itself. And there's options for this post to be even thicker and stronger should your wind load require it. So for regions which are exceeding 3 kPa or even 4 kPa, so say for example cyclonic regions near the coast. Now, looking at this joint, it is essentially a notched steel post section fit inside a sleeve, which will allow up-down movement. Slots, as we've discussed before, to allow brick ties to be locked inside and allow the force transfer between the blocks and the steel post. So the anchors to primary structure in this diagram shall be assessed per project basis. And this is just a general detail for general walls. The slots for the wall ties, as we stated, which lock inside. Now, for the control joints, there's also, before I talk about control joints, for the stainless steel wind posts, there's also an option to use a proprietary system, such as the Ancon WP4 system, which has 304 and 316 stainless, so marine stainless if required, which can be bought off the shelf and fit to the breeze block walls as an alternative. So we either have our custom wind posts, as we've seen before, or we can use these proprietary stainless steel Ancon wind posts. So please refer to the Ancon guidelines for the engineering design of these ones, or shall be checked by a competent structural or facade engineer. Now for movement joints and control joints, a consideration that can be made is to either use an end wall detail, so cap it off one block from the post. So this is the top detail here, and then seal off with flexible sealant to allow that movement joint. An alternative is to use debonding sleeves, which is basically a little plastic sleeve which will stop the wall tie from bonding to the mortar and allow movement. And that will conclude our breeze block masonry walls, structural design and development. Thank you for listening.
Thank you, Olsen, for a great presentation. I'd now like to welcome our third and final speaker for today's discussion, Kathy Inglis, General Manager Technical and Innovation at Brickworks Building Products. Kathy is an experienced materials engineer with over 20 years in the building industry and leads the innovation team in Brickworks Building Products across brands including bricks, precast concrete, masonry, roof tiles and lightweight facades. Please join me in welcoming Kathy Inglis.
Thank you, Amanda, for that introduction, and thank you, Thomas and Alison, for your presentation on the design of breeze block walls. I'm going to cover off today a couple of case studies, looking at some examples of the breeze blocks and their actually application in the field. So all the work that Thomas and Alison has done has been put together in our breeze block manual. So this is a 90-page manual filled with all the design charts and information you need to design any breeze wall block that takes your imagination. So architects are using breeze blocks for all of their benefits. They're low maintenance, they're all weather resistant, can be used in any climate zones, they're fire resistant and non-combustible, they're termite resistant, very simple installation, and they're environmentally sustainable. The breeze blocks are made in our factory at Gympie in Queensland. And this factory, we've just done our EPD, our Environmental Product Declaration, the first one on any masonry products in Australia or New Zealand. So you can look at the EPD and assess how they compare to other products. And they're also impact resistant. The range of breeze blocks covers 7 different shapes, and these come in the different formats and sizes that have already been covered, but they come in 4 colours as well, so you've got a choice. So these breeze blocks can be used individually or combined together in different formats to develop walls that will suit the architect's design intent. So there's 7 concrete products. In addition to the concrete masonry blocks, we have a clay breeze block. This is the Kite Breeze, and these breeze blocks are made in Italy and they come with a glazed finish on them. So they're a terracotta body, there's a white glazed, a salmon matte glazed and a terracotta glaze. At the moment, these blocks can't be used in exposure grade situations, but we're gradually working on the glaze to improve it to see if we can get them to be an exposure grade product. And when you're looking at where you can use breeze blocks, you need to look at not just the engineering design chart, will it stand up, but also the properties of the blocks, whether they're exposure grade or general purpose, or whether, so that limits their application, and what the properties are. So in the manual, there's a table list of properties of the masonry blocks with what their dimensional categories are, their core volumes, the shell thickness, and the characteristic unconfined compressive strength. So because these blocks are hollow and they have the porosity, their actual compressive strength of the units isn't great. So that needs to be taken into account, working out load bearing for the walls if it's required. So designing with the breeze blocks, what can be built? Obviously, there's a lot of imagination brought into this world by architects and what they want to do. They want the lightness and screening of a breeze block. They don't want to see large areas of restraint and reinforcement around the products. They actually want to have the lightness and screening properties of the blocks without the heaviness of solid walls around them. So often we see drawings coming in from architects that are just these floating screens of breeze blocks with nothing supporting them. And that's where the engineers are going to come in, and that's where all of you come in, to actually work with the architects to help them be able to design these breeze block walls so that can actually be structurally sound and carry the loads that they're intended to do. So to try and make it a bit simple, in the manual, we've actually got a flow chart of design. So all the steps that went through from Thomas and Alison, there's a little flow chart that steps through it. So what bond pattern are you using? What height's your wall? Are you having horizontal reinforcement? What is the wind load? And you go down the flow chart to work out which design charts you need to use for your situation. As I said, there's many options given. There's walls with stretcher bond that can actually span a lot further than the stack bonded charts. We've got reinforced stack bonded walls with either steel posts or with the reinforced block columns either side. So this flow chart will give you an idea of which pages to go to in the manual to look up the design charts. So now looking at a recent project that's just under construction. So this is Aria at Kangaroo Point in Brisbane, designed by Bates Smart Architects. And this project has breeze block screens on the balcony levels of this 7-story building. So these actually have quite high wind loads. It's a quite exposed building. So there is quite a significant wind load on these panels of blocks. They do range in size, in width. And when we looked at this, we working with the architects, it needed reinforcement in them. And this was the early days before we had the breeze block manual. So with looking at using structural steel to be able to support these breeze block walls. So these are some of the early concept drawings where we looked at a range of things. So incorporating Ancon with their ties and connectors for masonry, and incorporating those into the breeze blocks to be able to support this wall structurally. So there's a number of options put in place. Now, they also wanted this breeze blocks to be 70 mil thick. We actually don't have a 70 mil thick breeze block, so they wanted to get the 140 wedge breezes, cut them in half so they get double the output of the blocks as well, and use that. So once we've gone down to a 70 mil footprint for the wall, it's really quite narrow. So they needed some significant structural steel to be able to support it for those wind loads. So when doing, and also they wanted them stack bonded. So looking at a steel post between the blocks, this required the AMR horizontal bed reinforcement in every bed course, and then interlinked with the wind post depending what the wind load was and the size of the span of the breeze blocks. So this is with top connections into above and into the base, as has already been covered, the detailing of this. But it was a simple way to do it. So originally the concept was it was custom-made steel posts, and then Ancon came to the party and worked with the architect and to come up with the Ancon wind post to use for this project. So when using the Ancon wind posts, there's depending on the thickness of the steel and the depth of it. So as these blocks are only 70 mil, the steel isn't very deep through the depth of the wall. So they actually needed thicker steel to be able to carry the loads for those breeze block sections. Some of them were quite narrow. They were only 3 blocks wide, then 4 blocks wide, and there was a couple that were 5 blocks wide. But it was able to be done with the wind post and using those masonry tie connectors that run through the product. This is now under construction, and here's some of the images from the project. You can see there the blocks being laid, some of the steel around it, but it's essentially a steel frame around each section of the blockwork on the balconies. Some of these had to also deal with barrier loads and had a little bit of extra reinforcement included in them. But using a range of the masonry connectors, it gives you the ability to design around it. On the ground floor, they actually used the restraint to the concrete columns. So to the precast columns, you can have run the restraint up, and then the wall ties will sit into that. For the intermediate vertical posts, you can see that centre image there has the wall tie that's placed through the opening in the wind post and then turned so it flat and bears on the block surface. There was also another option where they looked at a head connection detail to the concrete plate running off an L angle bracket at the top with connectors down into the blocks, into the perpen joints. So there's lots of options that can be looked at depending on the design of the units and what the overall appearance you're trying to achieve. One of the other methods covered was using reinforced block work. around at the perimeters of your breeze block section. And depending on the block width and how big the reinforced blockwork is each side, of how far the wall can span. So again, these are horizontally spanning with reinforcement in the bed joints and the concrete blocks each side. So these are concrete blocks that would be the similar width of the block that your breeze block is. You put the 5mm horizontal bed reinforcement in every every horizontal joint, and the reinforced block columns have 2 N12 bars into the columns, and they're core filled, and that will provide the support. So in the manual, it covers charts that are with 1 block wide, 2 block wide, 3 block, and up to 4 blocks wide. So you can increase the span of your breeze block sections of wall. And it actually looks quite good with the sections of solid masonry and the breeze blocks. And it will depend which one it is, what you do. But there's charts for all of those covered in the manual. So what do you do if your breeze block wall that the architects conceived is not covered in the manual? And I have to say, we get sent images like that one there regularly going, well, look, that's got no structural support. I don't need any structural support. It just all goes together. Well, as you would have heard from the previous presentations, you actually do need that structural restraint in the wall. You can't just have an endlessly high and endlessly wide breeze block wall. As much as lovely as that would look, it's just not physically possible. So when the wall's not covered in the manual, there's a lot of ways it can be done. This is a current project we're working on again in Brisbane, up in Toowong, and this is designed with the wedge breeze, which is one of the wider base blocks, so it's got a bit of capacity. But they're now working through all the options of how to restrain this to the building and how to get structural capacity. So they're looking at a range of steel posts and what they can and can't use to be able to support this. Again, the first concept of this was just this thin veil that wrapped around the building with no solid connections at all. Now they're tweaking it to make sure the design can actually work. We also get projects where this is an exposed coastal headland and the architect's drawn in the kite breeze blocks, which are only general purpose grade, so they can't actually be used in a coastal severe marine environment because they're not going to withstand, they don't have the durability at this point to be able to be used in that application. When you're looking at designing breeze block walls, there's other things you've got to consider, and impact loads, barrier loads, but also in your design, looking at other restraints that may be necessary with, say, climbing. If a wall's right behind a pool, I can imagine lots of children just climbing up that breeze block wall and then trying to jump into the pool. So elements of the design for safety, because the breeze blocks do provide a platform for climbing as well. So it just needs to be taken into the scope of the project to make sure that it's covered in safety and design. Getting applications for curved walls. Now, obviously, the blocks are rectangular units. They're 390 long, or some are 290, some are 390. Quite hard to curve longer units wrap around a nice curved shape. So there's a potential on curves to actually install the breeze blocks vertically so that you can actually get a tighter radius around the curve. It is possible to look at wedging the mortar joints slightly to get a slight curve as well. But there's some walls that just aren't going to be feasible. And I know this is a small one, but this to curve around those tight things on a street level fence that permits climbing, and well, it's got one bit of concrete in the middle of it. The rest they didn't want to see any concrete supports. They don't want steel supports. Essentially have to go and tell them that this wall can't be built as it's drawn. You could need to go back to the drawing board, have a look at some other ways to restrain that wall. But if you're looking at walls that are outside, at the end of the manual, we actually cover off all the design parameters of the blocks. So for each block, it gives the dimensions, the mass, the section properties, all the things you need to be able to actually design your own restraints and your own wall depending on the specific circumstances of your project. Continuing on with the parameters, this is the reinforcement for reinforced block parameters for the when you're using reinforced blocks and reinforcement. There's also the equation for working out the reinforced blockwork column designs for the force equilibrium. So all the information is in the manual that you can actually design and feature your own blockwork, and it covers all the options. So thank you very much for your time this evening.
Thank you. A big thank you to our presenters today, Kathy Inglis, Olsen Lee and Thomas Chan. As always, it's now your turn to get involved. And please send your questions through via the YouTube chat box, saying who you wish to answer and where you're watching from would be nice too. And also a big thank you to everyone that sent through questions when they registered for tonight's event. I might start with you, Kathy. We've had a question that's come in asking you, Kathy, what is the thinnest wall thickness you can achieve in a breeze block?
Thanks, Amanda. It does depend on the design and how big you want the wall to be. But as far as manufactured blocks, the skinniest ones are 90 mils. I did explain the example where they cut the 140s down to be 70 mil wide. You wouldn't want to go any narrower than that. That'd probably be the absolute minimum just for slenderness and to get some sort of capacity in the wall.
Thanks, Kathy. And just saying what a beautiful studio. So our speakers are actually in Brickwork Sydney studio, which looks amazing. Olsen, just bringing you into the conversation, we've had a question, can programming help in the design?
Yeah, just with any engineering design, computer tools such as custom-made programs or software packages can always use to accelerate the design process. Now, just a little bit more insight into these charts and how they're developed. They were developed using programming and macros, Visual Basics, and so on. So that means that whatever additional tools that are developed will be definitely helpful. I mean, if you're designing walls in large quantities. Otherwise, traditional hand calculations or bespoke simulations will also work.
Thank you. Thank you for that. A question for you, Thomas. What height wall requires footings and is sizing of footings as per block walls?
Thank you, Amanda. I think this question depends on a few considerations. One, of course, as said in the question, is about the wall height. And second is about the ground condition, which is the bearing strata conditions. And the third is the magnitude of the wind. So say if you have a higher wall height, probably you need a footing rather than a short height of wall. And also if you have a larger wind magnitude and combination with a certain height of wall, you may have a problem on the overall overturning effect on the wall. And then you may need a footing on the wall, under the wall to overcome this overturning effect. And if you have, say, a soft soil material to support this wall, or even a clay, which is a reactive for swelling effect, then you may need a footing to spread the load from the wall or control the differential settlement. But if you have a rather strong strata like rocks, then you may minimize the footings and also minimize the footing depth as well. So for the engineering wise, you need to consider all these combination effect to find out whether you need a footing or not for a brick wall.
Thanks for that. Thank you. We've had a great question that's come in, and maybe Kathy, we can start with you, and then also you may want to comment as well. And the question is, Kathy, we have clients that like a variety of blockwork and cladding outcomes. How can this be designed?
It is possible to use different materials together. So it could be breeze blocks, normal concrete blocks, clay bricks, lightweight cladding together, but they do need to be separated structurally, and the structural support depending on each material, what that needs to be. So you might need a little bit more support where you've got the heavier units compared to a lightweight cladding, but they can essentially run up to each other. And just usually between them, you'd probably need an articulation joint to deal with the change in thickness or change in structure. Wouldn't that be right, Alison?
Yeah, that's right. Yeah, so just as Kathy said, the possibilities are really endless with all these breeze block products and the way you arrange them, especially with other systems such as cladding or windows, say, for example. Now, the design of these would recommend that they'll be designed as separate engineered systems and requiring control joints, as Kathy said, to minimize the effect on each other. But if it really comes to the stage where you need one system to support another system, then we highly recommend that you get a qualified structural engineer or a facade engineer just to have a look and just to make sure it's structurally sound for the application that it's intended for.
Thank you, thank you. Our next question has come in and it's in two parts. So I might put the first part of the question to you, Alison, which is, what is the strength of these walls as compared to normal brick walls?
Yeah. So as with lots of things, the answer is it depends. But in general, the strength of breeze block walls are less than traditional masonry. Now, the behavior which should be, or the behavior that dominates this effect is the depth of the wall. So the thicker the block, the stronger it will be. And it's the same for a traditional brick wall. The thicker the brick wall, the stronger it will be. Now, as a comparison in general, so if we're talking about stretcher bond, breeze block walls perform slightly poorer due to their slightly weakened failure planes, as we've discussed in the presentation. But that can be compensated using a high grade of mortar, say for example, or sorry, I lost my chain of thought there.
Reinforcement?
Yeah, or reinforcement. That's right. That's right.
Thanks for that. And the question goes on, Kathy, to the height. What height shall be used to start these walls from the ground from a safety point of view while using above ground floors? Kathy.
The height to start the breeze blocks depends on the application. Again, it's specific to each project. So to consider safety in design, is it going to be climbable? Is it somewhere where there's access for children or adults, to say that they could do it too, to actually climb up the walls and add significant load, but also to injure themselves by falling afterwards. So to consider the safety in design, so on a ground floor, you might not want to start them below a normal balustrade height where you facilitate climbing. It might be above that. And that, again, gives you a solid wall that could be your base for restraint for your breeze blocks above that. It's going to vary application by application. Once you get above ground floor, it's probably not as critical to look at that unless they're balconies where you, again, have the possibility of climbing and people injuring themselves by falling.
Thank you. And we've got a question coming for you, Thomas, from Anthony, who's asking you, what material is the Rio? Any concerns for durability and corrosion?
So the reinforcement is the proprietary product from Angan, which is a stainless steel. So it's pretty high resistant to corrosion. So it has a pretty strong durability in the design life of the breeze block walls.
It's also got the cover from the mortar, so it's set in the middle, so you do get cover protection from the mortar.
Yes,
same as
of course.
So from the reinforcement in the block cores and things.
Same,
similar.
yeah, similar.
So just to add on that, it will generally achieve the 50-year design life, given that you are not in some heavy industrial pollution zone.
Thanks. And a quick fire questions come in. Is hit and miss breeze block possible? Alson?
Yes, the answer is yes, as with most things. But what is the capacity that we can get from this kind of arrangement? Now, hit and miss masonry, there's lots of creative ways that we can use the support. Now, traditional masonry, just like solid clay brick units, which are hit and miss, we generally use some sort of rods which are stuck through these alternating planes, just to kind of reinforce it vertically down. This is a special case for the breeze blocks because they don't really have space for that kind of reinforcement, or if we were to look into our application, we might need to modify the breeze blocks slightly to cater for this. Now, as for what kind of capacity we kind of expect for hit and miss breeze blocks, as long as the wall is small enough, I suppose we can use hit and miss design. Now, there's a great document from Thick Brick which goes through the technical aspect of this. So I encourage all the viewers to look at this document for the design. It will be similar for small walls, but for larger walls and just scaling external conditions, which are using in high wind zones, say, for example, it must be looked on a case-by-case basis by a qualified engineer.
Thank you for that. And Kathy Syed sent a question in for you. What is the most significant benefits of such brick wall design?
I think the main benefit of a breeze block wall is to provide ventilation and screening. So it gives you some form of privacy, but also allows ventilation. I think that follows on from the hit and miss as well. Hit and miss with solid clay bricks is done to give you those openings and allow breeze and to create pattern and texture. The breeze blocks do that by themselves. You actually probably really don't need to do hit and miss with them because you have actually got the openings with the porosity that allows that breeze path ventilation and some privacy screening with the products themselves. And of course, architects just love to do anything different with be creative with products and come up with those weird and wonderful designs that all of you as engineers need to figure out how to actually build them.
Yeah.
Well, the structural engineers that are listening.
And I can see Olsen and Thomas nodding away at that. Do you want to add anything to that, Thomas? Olsen?
Yeah. So for just for any strange, weird, and wonderful design not covered by the manual, an engineer is definitely the way to go. Yes, especially if you're looking for a structural. So I mean, in general, if it's a non-structural wall, say for example, just in a garden or whatever, not posing any threat to human life, it does not specifically needs to be an engineered system. But in terms of talking about a structurally engineered and a certified system, they definitely need an engineer.
Thanks, Olsen. And just staying with you for now, questions come in. Is the crack pattern similar to RC slab yield line theory? Olsen.
Yeah, definitely. So in terms of the theory, it is definitely extremely similar. So reinforced concrete yield line theory, or even say, for example, like a flat plate of metal where the yield lines will develop for that one, the plastic hinges. This theory is almost identical in terms of the location. Now, for the mechanism of failure, it is also similar but slightly different. The details of which probably are beyond the scope of this presentation.
Thank you. And just staying with you again, Olsen, Chris, good afternoon to you. He sent through a question saying, how much of a difference the M3 mortar would have on it if all the tables are based on M4 mortar? Hopefully that makes sense.
Yeah. So in our testing regime, most of the products, I believe, I think all but one of our test samples were using M4 mortar or product-based equivalents. Only one test was using M3 and it underperformed by a small margin. Now, due to the performance of the breeze blocks and how we want to achieve a maximum capacity, especially in different or across all climate zones and all corrosion zones in Australia, we've elected to use M4 mortar because of requirements from 3700 for durability and for strength purposes. Now, as to answer the question, how much of a difference would it actually make? For the unreinforced capacity, I would expect there would be at least a 10% difference. Now, don't quote me on that one, but the range will be definitely in that zone. And for the reinforced capacity, we just recommend that you use M4 mortar for the enhanced compressive strength and for the bond to the reinforcement and to make sure that we get that stress development.
Thank you, Olsen. And I might just ask a question on behalf of Engineers Australia to you, Kathy. Obviously, we're in the middle of a major infrastructure boom across the country. What sort of in breeze block design, what sort of trends do you see emerging? What do you predict for the future?
It's interesting. I mean, breeze blocks have been around for generations, like decades, and I think they were originally used mostly in council toilet blocks. I think was the main use of just a couple of rows of breeze blocks up the top. You know, the big full size of them. As you walk around the old Sydney and the older buildings, you see little random bits of breeze blocks. You know, there'll be one in the middle of a balcony wall or a couple little bits. With the range of shapes and the quality of the mix we have now to have these polished breeze blocks, it just gives it that level to take it to the next quality level, to be able to create more, I suppose, architecturally aesthetic walls that people want to see more of, not just have one or two blocks here and there, but actually see whole walls of them. And as we try to design for the changing climate and have access to breeze and ventilation in our homes, but also some privacy, breeze blocks are one of the perfect products to be able to do that. And as we said, you can, creative as you want, you can mix some of them together as long as they're the same width. You can double them up. You can, the kite breeze that are here, you can alternate them in different patterns to create shapes, shadows, and different texture to your wall. So I think the possibility is endless. And as the interest in them starts to grow, we'll probably start to develop some more shapes in the range.
That's exciting. Thank you. And I just wanted to sort of finish up because, as always, we've pretty much run out of time. Maybe Thomas, you know, our young engineers out there that are starting out and want to know more, what advice would you give them? Where to go, how to find out more information?
Want to find out more information?
Advice for young engineers.
Advice for young engineers.
Yes.
So of course attended Australia Engineer Australia's seminars like this. Yeah. Yes. Yeah, a lot of that. So this very good chance to learn a lot of the new technologies, new knowledge, and also the latest market trends of Australia. So there's a very good chance, and definitely this free of charge. Very important. So Alison, do you have any addition to that?
Oh, young engineers. Oh, I can't really.
You're a young engineer.
Yeah,
Come on, you're a young
engineers.
engineer.
Advice? I don't know. It's just really
Or your experience?
my experience. Oh, it sounds so stereotypical, but really, you just have to get out there and just So when you're engineering systems, really just look through all the material. Go to your colleagues and your mentors. They're really a trove of knowledge. And just a little bit of a side note: the Australian Standard supplements are actually a great material and a great document for you to go through if you have the patience. But they contain so much information, especially on the basis of the standards and how they're developed. Because initially when you look at a standard, it just looks like a bunch of numbers and formulas with nothing much behind it. But there's behind each clause, there's logic, and someone's thought through and done research on this topic, which is quite often written in the supplement. And then those, of course, they have their secondary sources, and then the research papers if you're willing to go through them.
But in those research papers that form, particularly say AS 3700, which breeze blocks, one of the main standards we look at, the research papers that underpin a lot of the changes and updates to 3700 over the years have been done by the brick industry, and all those research papers are actually on the Think Brick website. It's interesting. I've sat on that standard for, I don't know, more years than I can count. And the researchers at the University of Newcastle in the structural engineering, civil engineering department have done that research that underpins the changes. And the most recent addition was the stack bonded brickwork that went into 3700, which formed after a basis of 4 years of research on testing stack bonded walls in practice in the labs up there and doing all the calculations. So good. The industry websites are a great place for resource. Yeah.
Yes.
Thank you, and thank you for that. So thank you. Let's all get out there and do it. So it is all we have time for today. Once again, please join me in thanking our speakers. A big thank you also to our industry partner Brickworks for their ongoing support. And I look forward to seeing you at our next Thought Leaders event. Thank you and good evening.